the derating required for the secondary feeder running in an underground duct bank is correct. The insulating properties of the ground can indeed cause the cables to overheat, which can lead to a fire hazard. The number of cables that seem excessive is often necessary to ensure that the cables do not overheat. One way to approach reducing the number of cables is to explore different cable types. For example, consider using cables with a higher insulation rating. This allows you to achieve the same level of protection, but with fewer cables. Another approach involves modifying the duct bank itself. A duct bank with a higher thermal conductivity can significantly improve heat dissipation from the cables, thus reducing the risk of overheating. If you cannot effectively reduce the number of cables or improve heat dissipation through cable or duct bank modifications, installing a dedicated cooling system for the duct bank is a viable option. This will help keep the cables cool and prevent overheating. Consider these additional ideas. Firstly, using a different type of transformer, such as a transformer with a lower secondary voltage, which reduces the secondary current and subsequently the number of cables needed. Secondly, assess the possibility of installing the transformer in an alternative location, such as a fault or a substation. These locations generally offer better ventilation and cooling capabilities. Thirdly, increase the physical size of the duct bank. This provides more space for the cables, allowing them to dissipate heat more efficiently. The goal is to manage the heat generated by the high secondary current of the 1300 kV transformer, which in your case is 4164 amps at 120/208 volts. When dealing with underground duct banks and the associated derating factors, several key aspects must be considered to ensure the safe and efficient operation of the electrical system. These considerations involve understanding ampacity derating, cable selection, duct bank design, and applicable standards. The ampacity of a cable is its current carrying capacity under specific conditions. Underground installations, especially in duct banks, often require derating the cable ampacity due to the reduced ability to dissipate heat. The National Electrical Code (NEC) provides guidelines for ampacity derating based on factors such as the number of conductors in a raceway or cable, ambient temperature, and soil thermoresistivity. Accurate calculations are crucial to prevent overheating and potential failures. Various types of cables are available, each with different insulation properties and temperature ratings. Selecting the appropriate cable type is critical for underground duct bank applications. Cables with higher temperature ratings, such as those with cross-linked polyethylene, XLPE, or ethylene propylene rubber (EPR) insulation, can withstand higher operating temperatures and may require less derating. The physical design of the duct bank significantly impacts heat dissipation. Factors to consider include the spacing between ducts, the material of the duct, and the backfill material used around the duct. Materials with higher thermal conductivity, such as concrete, can improve heat dissipation compared to materials with lower thermal conductivity, such as PVC. The depth of the duct bank and the surrounding soil conditions also play a role. Standards such as the NEC and IEE standards provide detailed guidance on designing and installing underground duct banks. These standards outline requirements for ampacity derating, cable selection, duct bank construction, and grounding. Compliance with these standards is essential for ensuring the safety and reliability of the electrical system. When calculating the required number of cables for each phase, consider the following steps. Firstly, determine the total load current. Calculate the secondary current of the transformer using the formula I equals S divided by the square root of 3 times volts line to line, where I is the current, S is the apparent power in voltamps, and volts is the line-to-line voltage. For a 1500 kV transformer with a 120/208 volt secondary, the calculation is 1,500,000 voltamps divided by the square root of 3 times 208 volts, which equals approximately 4,164 amps. Secondly, determine the ampacity of each cable. Select a cable size and insulation type and determine its ampacity from the NEC tables or manufacturer's specifications. For example, a 500 kilocircular mils copper cable with 90 degrees Celsius XLPE insulation might have an ampacity of around 470 amps under certain conditions. Thirdly, apply derating factors. Apply all applicable derating factors based on the number of conductors in the duct bank, ambient temperature, and soil thermal resistivity. The NEC provides tables and formulas for calculating these derating factors. For instance, if the derating factor is 0.7, the adjusted ampacity of the cable would be 470 amps times 0.7, which equals 329 amps. Fourthly, calculate the number of cables required. Divide the total load current by the adjusted ampacity of each cable to determine the number of cables needed per phase. In this case, 4,164 amps divided by 329 amps equals approximately 12.66 cables. Since you cannot use a fraction of a cable, round up to the nearest whole number, which is 13 cables per phase. This calculation assumes a specific set of conditions and cable properties. It's important to consult the NEC and engineering guidelines to account for all relevant factors and ensure accurate results. To mitigate the need for an excessive number of cables, consider the following strategies. Firstly, optimize duct bank design. Use materials with high thermal conductivity for the duct bank and backfill to improve heat dissipation. Ensure adequate spacing between ducts to allow for better ventilation. Secondly, use higher temperature rated cables. Cables with 90 degrees Celsius insulation can handle higher operating temperatures and may require less derating. Thirdly, implement forced cooling. Consider using forced air cooling or liquid cooling systems to remove heat from the duct bank. This can significantly increase the ampacity of the cables. Fourthly, reduce load current. If possible, reduce the load current by optimizing the electrical system design or using energy-efficient equipment. Fifthly, use multiple smaller transformers. Instead of one large transformer, use several smaller transformers to distribute the load and reduce the current in each feeder. Sixthly, consider direct burial cables. Direct burial cables can sometimes offer better heat dissipation compared to duct banks depending on the soil conditions. Seventhly, use aluminum conductors. Aluminum conductors have a higher ampacity to weight ratio than copper conductors, which can reduce the number of cables required. When selecting cables for underground duct banks, consider the following cable types. Firstly, copper conductors. Copper is a widely used conductor material due to its high conductivity and corrosion resistance. Copper cables are available in various sizes and insulation types. Secondly, aluminum conductors. Aluminum is a lighter and less expensive alternative to copper. Aluminum cables have a higher ampacity to weight ratio but require larger conductor sizes to achieve the same ampacity as copper. Thirdly, cross-linked polyethylene XLPE insulation. XLPE is a thermosetting insulation material with excellent electrical and thermal properties. XLPE cables are suitable for high-temperature applications and offer good resistance to moisture and chemicals. Fourthly, ethylene propylene rubber EPR insulation. EPR is a synthetic rubber insulation material with excellent flexibility and electrical properties. EPR cables are commonly used in underground and wet locations due to their resistance to moisture and ozone. Fifthly, polyvinyl chloride (PVC) insulation. PVC is a thermoplastic insulation material with good electrical and mechanical properties. PVC cables are commonly used in low-voltage applications and are resistant to chemicals and abrasion. When designing the duct bank, consider the following factors. Firstly, duct material. Use duct materials with high thermal conductivity, such as concrete or fiberglass, to improve heat dissipation. Avoid using PVC ducts, as they have lower thermal conductivity. Secondly, duct spacing. Maintain adequate spacing between ducts to allow for better ventilation and heat dissipation. The NEC specifies minimum spacing requirements for ducts in underground installations. Thirdly, backfill material. Use backfill materials with high thermal conductivity, such as sand or gravel, to improve heat dissipation. Avoid using clay or other materials with low thermal conductivity. Fourthly, duct bank depth. Install the duct bank at a sufficient depth to minimize the impact of surface temperature variations. The NEC specifies minimum burial depths for underground cables and raceways. Fifthly, duct size. Select duct sizes that are large enough to accommodate the cables and allow for future expansion. The NEC provides guidelines for conduit fill ratios. In addition to the number of cables and duct bank design, consider the overcurrent protection for the transformer secondary. The 5000 amp fusible switch in the switchboard provides overcurrent protection for the secondary feeder. Ensure that the switch is properly sized and coordinated with the transformer and cable opacities. The overcurrent protection should protect the cables from overload and short circuit conditions. Coordination studies are essential to ensure that the overcurrent devices operate in the correct sequence and prevent nuisance tripping. Furthermore, consider monitoring the temperature of the cables and duct bank to ensure that they are operating within safe limits. Temperature sensors can be installed in the duct bank to monitor the cable temperatures. Alarms can be set to alert personnel if the temperatures exceed predetermined thresholds. This can help prevent overheating and potential failures. Remember to consult with qualified electrical engineers and follow all applicable codes and standards to ensure the safety and reliability of the electrical system. The NEC is a valuable resource for guidance on ampacity derating, cable selection, duct bank design, and overcurrent protection. Also, you may want to consult IEE standards for additional information on underground cable installations. Finally, ensure that all work is performed by qualified and licensed electricians. Regular maintenance and inspections are also crucial for maintaining the integrity of the underground cable system. This includes checking for signs of damage or deterioration, testing the insulation resistance of the cables, and verifying the proper operation of the overcurrent protection devices. By carefully considering all of these factors and implementing appropriate design and maintenance practices, you can ensure the safe and reliable operation of the underground duct bank and transformer secondary feeder.